All right, so a little renal acid-base physiology. So first of all, what are the two types of acids in the body? Well, you got volatile acid and non-volatile. Now, a volatile acid would be something like CO2. Carbonic anhydrase, now, we're going to talk about that here in a second, but for right now, I just want you to know that CO2, a lot of people don't know CO2 is an acid, so how could CO2 be an acid? And this kind of gets into the next slide, but think about that. Well, CO2 is a gas and it can cross the blood-brain barrier, and what happens is it combines with water to form carbonic acid, then carbonic anhydrase dissociates it into H plus and bicarbonate ions, and that H plus is how CO2 is considered an acid. So carbonic anhydrase, let's write that reaction out. CO2 plus water yields carbonic acid, which yields H plus, that's how it's an acid, plus bicarb. So you get an acid and a base out of carbonic anhydrase, which works right here. Or actually right there, that step. So let's talk about some non-volatile acids or fixed acids. Sulfuric acid is one. Phosphoric acid. And that would be H2SO4 or H3PO4. We're going to get into those also. So some other fixed acids can be overproduced in disease or may be digested. So let's give some examples of those, like keto acids and diabetic ketoacidosis. Keto acids, how about lactic acid? Exercising too much, building up lactic acid in the muscle. And how about even a salicylic acid, aspirin? Um, Now let's talk about buffers real quick. Buffers, what buffers do is they prevent a change in pH when the H plus ions are added to or removed from a solution. They're most effective within 1 pH point of the pKa. Most effective when within 1 pH point of the pKa. So what is the major extracellular buffer? It's got a pKa of 6.1. It's bicarbonate. Another minor extracellular buffer would be phosphoric acid. HPO4 minus. But bicarbonate is by far your major extracellular buffer. Phosphate is more important as a urinary buffer, which we will see why later on. So like excretion of H plus ions, if you want to excrete acid in the urine, this right here would become H2PO4, and that's called a titratable acid. That's all that means. When you hear titratable, you're titrating the pH of in the urine right here with this HPO4 minus to become phosphoric acid, and that's how you excrete it in the urine. So what is the major intracellular buffer? Take a minute and think about that. It's hemoglobin. Intracellular buffer. In the physiological range, deoxyhemoglobin is a better buffer than actually oxyhemoglobin. So definitely need to know that. Now the Henderson-Hasselbalch equation, which reads pH equals the pK plus the log of the acid over the titratable acid. Now, what I want you to do, and just trust me on this, is go ahead and forget about all of that. And what we're going to do is a little trick that Dr. Francis shows you. When the pH equals the pKa, you're 50% dissociated, okay? Now, if you go 1 pH point above that, this is called the 1, 10, 50, 90, 99 rule. So what that means is whenever the pH equals the pK, you're 50% dissociated. Now, you have to also look at this on a little scale here. Sorry. So you have to have this in mind. So you see these two right here. You see this plus and you see this minus. This right here is called the titratable zone or the buffer zone. So that right there is anything that's water soluble. So you need to know that all bases start off charged and all acids start off bioavailable or uncharged. All bases start off charged, all acids start off bioavailable or uncharged. Now, from there, all you got to do is look at this rule here. So if I told you you had ingested an acid like aspirin, and its pKa was 4, you could look at this and tell me when it would be bioavailable depending on the pHs of the stomach, depending on the pH of the duodenum, depending on the pH of the jejunum, etc. So if you have a pH of, or a pKa of 4, what's the pH of the stomach? It's about 2. So you're 2 points below your pKa. That means you're only 1% dissociated. And I told you that acids start off bioavailable, so that means 99% of that acid is going to get across in the stomach, and that's why acid can burn a hole in your stomach. So, and you can use it. You can use that 50 different ways, but that's just a nice little thing to know. Just know that when the pH equals the pKa, you're 50% dissociated. All right, so finally, acid-base disorders. Let's talk about these. Some definitions, first of all. What's an acidemia? Well, it's a pH below 7.35. An alkalemia is a pH above 7.45. A respiratory acidosis is a PCO2 greater than 45 millimeters of mercury. And a respiratory alkalosis is a PCO2 less than 35 millimeters of mercury. So we're going to make a little chart here for metabolic acidosis, metabolic alkalosis, respiratory acidosis, and respiratory alkalosis. I'm going to have the pH right here. I'm going to have the PCO2. I'm going to have the bicarbonate. and we're going to have the compensatory response. Look at how all these affect each other. All right, so you know if you have we'll start with the acidosis first. If you have a metabolic or respiratory acidosis, your pH has got to be down. So you can already go ahead and know that much. Now, remember I told you CO2 is an acid? So if you have a respiratory acidosis, you go ahead and know that the PCO2 is up because PCO2 is an acid. So in metabolic acidosis, you know that's got to be down. Now, let's talk about bicarbonate. In respiratory acidosis, if you have a lot of PCO2 floating around, what do you want the bicarbonate to be? You want it to be up, you want it to buffer. So it's got to be up as well. Therefore, in a respiratory or a metabolic acidosis, the bicarbonate's got to be down because it's buffering too much of this acid. For whatever reason, you got a metabolic problem. Remember I told you bicarbonate is the major extracellular buffer. So what is the compensatory mechanism for metabolic acidosis? It's hyperventilation. What about for respiratory acidosis? That would be an increase in the renal bicarb reabsorption. Starting to make sense? I hope so. All right, so now we're going to go on to the alkalosis. Metabolic alkalosis and respiratory alkalosis. Right away, you know that the pH has got to be up. So, respiratory alkalosis, PCO2 is an acid, therefore it's got to be down. Therefore, in metabolic alkalosis, the PCO2 has got to be up. Now, the bicarbonate, this one confuses people sometimes. The bicarbonate in respiratory alkalosis has got to be up or down. It's got to be down. And it's got to be up in metabolic alkalosis. Why would the bicarb be up in metabolic alkalosis? Because it's not buffering any of the acid, right? Good job. You got too much bicarb floating around. That's why you're metabolically alkalotic. So, with that said, what is the compensatory response of metabolic alkalosis? Hypoventilation. We want to hold on to some of the PCO2. It's an acid. What about respiratory alkalosis? What's the compensatory response? You want to decrease renal bicarb reabsorption. So that is how you figure those out. And the way I do it, you can do this many different ways, and whatever works for you, just stick with that. The way I do it is to always think PCO2 is an acid. If you tell me, you got to tell me the pH from the get-go, or I can go ahead and guess it, depending on the patient's symptoms. So then you automatically know what these other labs should look like. And if it's not looking like that, then there you got a problem. So it's literally that simple. Winter's formula. All right, let's talk about Winter's formula. So what Winter's formula is all about knowing if something is, it's respiratory compensation in response to metabolic acidosis, and you can quantify it with Winter's formula, which is PCO2 equals 1.5 times the bicarbonate plus 8 plus or minus 2. So Winter's formula is used to measure the appropriateness of the compensatory response and to evaluate for a mixed acid-base disorder. okay, which a lot of time people have in the real world. So if PCO2 is within the expected range, then the respiratory response would be adequate. Respiratory response is adequate. Now, if the measured PCO2 is higher than expected, you have an additional primary respiratory acidosis. What about if the PCO2 is lower than expected? You have an additional primary respiratory alkalosis. So now we're going to talk about the serum anion gap acidosis, or gap acidosis, you could also hear it termed. So the serum anion gap is sodium minus bicarb plus chloride. So basically all we're doing is we're subtracting the positives from the negatives, and the two negatives we have are bicarbonate chloride out in the extracellular plasma or the serum, and the positive we have is sodium. So because potassium, remember, is intracellular. So this represents the unmeasured anions in serum and is normally 8 to 16 milli equivalents per liter. It's very important to remember that number. 8 to 16 milli equivalents per liter. The reference for what is considered a normal anion gap depends on the particular lab in real life performing the calculations when you order a basic metabolic panel. So just keep that in mind. All right, so mud pilers. What does mud pilers mean? Mud pilers is a mnemonic for an increased serum anion gap metabolic acidosis, like I said, also known as a gap acidosis. All right, it's associated with mud piles, and what that stands for is methanol, metformin, uremia, like advanced chronic renal failure versus early renal failure, which may cause normal anion gap metabolic acidosis. So if you're in advanced chronic renal failure, you're going to get more uremia. DKA, diabetic ketoacidosis. What are the two? Here's a little side note for you. What are the two things that the two acids you'll see in DKA? One is beta hydroxybutyrate, and the other one is acetoacetate. P stands for paraldehyde. Fenformin, iron, or isoniazid, lactic acidosis, So lactic acidosis, you could see that in shock, hypoxia, poor tissue perfusion, carbon monoxide, cyanide, et cetera, et cetera, et cetera. So the big one I like to remember is shock or hypoxia because you see that a lot. So someone climbing Mount Everest could definitely be in they could definitely have lactic acidosis, which would and lead to an increased serum anion gap metabolic acidosis or gap acidosis. Ethanol, ketoacidosis, drinking too much. Ethylene glycol. I just worked a step 2 question on this the other day. You'll see calcium oxalate stones in their urine. That's how you can tell. Rabido. Come on, computer, work with me. Rhabdomyolysis, one of our favorites. And salicylates. With a concomitant respiratory alkalosis. So, prolonged starvation, ketoacidosis also could be under that. So let me write that in for you. All right. Now we're going to talk about fused CARs, which stands for normal anion gap metabolic acidosis, also known as a hyperchloremic metabolic acidosis or non-gap acidosis. And the way we remember that is with the fused CARs. All right, so the F stands for fistula. Like in the small bowel or pancreatic fistulas, what happens is you have a loss of bicarbonate there. And that's why you get this normal anion gap metabolic acidosis or hyperchloremic because you got too much chloride. Ureterogastric conduits. I'm sure you're wondering what the hell that is. Like an example would be a urine diverting colostomy. You're also going to get a loss of bicarb there. Saline administration. Saline worsens metabolic acidosis. Can anybody tell me why? This is huge. Everybody misses this. This is very important because you're gaining chloride. Salt, sodium chloride, saline, 0.9 sodium chloride. Saline worsens metabolic acidosis. Don't give it. So then we get to the endocrine. Hyperparathyroidism, a cause of type 2 RTA. And also Addison's disease, which is an aldosterone deficiency. Diarrhea, loss of bicarb again. All right, so carbonic anhydrase inhibitors such as acetazolamide. This is the most common cause of type 2 renal tubular acidosis in adults. You're losing bicarb, okay? It's really that simple. So the CAR stands for carbonic anhydrase inhibitors. The A stands for acid infusion. Example, the main acid we use in medicine is ammonium chloride. So you get hyperalimentation with the TPN, or the total parenteral nutrition, if arginine hydrochloric acid or lysine hydrochloric acid are used as amino acids, because I wonder why that would be. You're gaining chloride. Okay? It's literally that simple. Just remember, you're gaining chloride, not good. Now we get to talk about the RTAs. So the ones that I want you to know is type 1, type 2, and type 4. Don't worry about type 3. So in type 1, you have a decreased distal H plus secretion. So you're going to get a hypokalemia with the urine pH greater than 5.5. In type 2, you have a decreased proximal, not distal, tubule bicarb reabsorption. Okay, so you can't reabsorb your bicarb. You're also going to get a hypokalemia, but now here's the difference. The urine pH is going to be lower than 5.5. Now in type 4, this is an aldosterone deficiency or resistance. You're going to get a hyperkalemia because aldosterone can't kick off the H plus in the distal tubule, so the urine pH is going to be less than 5.5. And the last one, spironolactone, blocks aldosterone receptors. Okay, and lastly, a normal anion gap metabolic acidosis is caused by loss of bicarb or gain of chloride. It's that simple. Both of which usually result in a hyperchloremic metabolic acidosis. When you hear that, that's what they're talking about. Loss of bicarb or gain of chloride, one of the two. A gain of chloride is usually compensated by a loss of bicarb. So you get a hyperchloremic metabolic acidosis. Now, a loss of bicarb is usually compensated by chloride retention, right? We're trying to keep the positives and the negatives in balance here. We're trying to buffer each other. And that results in a hyperchloremic metabolic acidosis. And that is acid base for you wrapped up.